Hmm. Oh.
Hey there, welcome to Introduction to Bioengineering at Stanford University. Did you know that bioengineering is the newest engineering major here at Stanford?
Yeah, it's the first major to get introduced since 1960. And that other major was computer science, which has been a pretty big deal.
Yeah, I guess. I mean, computers are important, but they only deal with bits, you know? And biology deals with bits and atoms, the stuff of life. And, that's what bioengineering is about. Now, of course, as the newest major, what does that mean? How old are we? 1960? We're not that old. We're 18 years old, like a lot of you, perhaps. That means you're part of the first bioengineering generation.
And we want to help you shape this bioengineering discipline. We want for you to become bionauts.
Bionauts?
Yeah, like astronauts, but for biology. By learning about bioengineering, we hope that you get the option of becoming a leader or an adventurer who can shape a future and do good in a future that's increasingly biotic.
I like how that sounds, a biotic future. Well, that's the framing of the course, but how's the course going to work? How are you going to experience it? How are we going to motivate all this hard work of learning? The first thing we're going to do is we're going to introduce you to bioengineering from accessible and pressing and important problems. Things like cancer. What can bioengineers do about cancer?
Cancel it.
Sounds good. How about infectious disease?
Make them obsolete.
Bioengineers, could we help with the food supply?
Yeah, we should make nutritious and cheap food for everybody.
Let's see, bioengineers, could we work with the doctors and medicines?
Yeah, let's make new medicines. Cure all the diseases.
Every disease?
Yeah, all of them.
All right. So what about nature? I hear things are going extinct more than ever before.
Well, let's fix that.
How are we going to fix that?
No medicines for our endangered friends.
Oh, medicines for animals?
Yeah.
Bringing things back from extinction?
Oh, also that. Okay.
Bioengineering beyond humans. Anyway, you get the idea. All these topics you're going to experience through this course, and we'll use these topics to motivate your learning around fundamental tools and skills in bioengineering.
Yeah, but here's where it gets really neat. You're going to learn some fundamental tools, things like how to manipulate and design DNA so that you can have an impact on all these different areas. There's a nice through line through bioengineering that allows you to make an impact in a lot of different spaces.
Because when you learn how to engineer biology systematically, it's sort of like learning how to program a computer systematically. You know, you could write a program for music or financial analysis or planning a bus route. You know, that skill set needed to program a computer is agnostic with respect to the applications. The same thing's going on today in bioengineering. By learning the fundamental skills and tools needed to work from inside cells out, you get a general purpose capacity to partner with biology to solve problems.
Yeah, by the end of this class, we hope that you'll have an understanding of the enormous impact that bioengineering is already having on people and the planet. We want you to learn how to read, understand, and debate what's happening in bioengineering so that you can be a leader and a citizen about all things related to biotechnology.
One of the parts of the class that's super important is because bioengineering is young, most of what you could do with it hasn't been imagined. Yes, we have plenty of compelling examples to help you learn, but most of what could be done in the future with bioengineering over your lifetime, nobody's imagined. And so an essential part of this course is you will have a project where you get to imagine what bioengineers could do. Something that's relevant to you wherever you are and how you see the world and what you wish the world to be. So this course project towards the end of the quarter will be a really essential and exciting component for the course.
We're really excited to be your guides on this journey from where you are now to the bio frontier.
How about us? Who are we, you might be wondering? Jen, What about you?
Well, I'm Jen Brophy. I'm an assistant professor at Stanford, and I teach classes, as you can tell, but I also run a research lab. In my lab, we engineer bacteria and plants in order to try to make them more resilient to climate change. I got interested in this when I was in college, where I read an article in the school newspaper about people trying to engineer biofuels and bacteria, and I thought that was really cool. It got me interested in bioengineering, and that desire to make a difference in sustainability has been motivating me ever since.
So cool. I am Jen's colleague, Professor Brophy colleague. My name is Drew Endy, also a professor here in bioengineering at Stanford. I love teaching this class, mostly because I can't wait to see what you're going to imagine to do with bioengineering to make the world more awesome. I don't grow up in California. I grew up in Pennsylvania. I loved nature, but when I was a high school student, I really struggled with biology. I hate memorizing things. It's like, oh my gosh, it just wasn't for me. But I do like to build things, and I do like to understand how things work. I thought I was going to become a civil engineer and work on roads and bridges. But over time, what I learned is that the best way to build something is to grow it. Biology is nature's builder. Anywhere on the planet, you can work with life to grow something with atomic precision into some big structure or whatever you want. And so that's why I've become a bioengineer, and gives you some sense of why this class is so exciting to me. In any case, the class is about you, and Professor Brophy and I are really excited to be able to work with you over the next few months to introduce you to bioengineering.
Yeah.
Bionauts Assemble!
Bionauts Assemble!
Welcome to Introduction to Bioengineering at Stanford University. Just a short video. What is our class about? Students completing the course will have a working understanding for how to approach the systematic engineering of living systems to benefit all people in the planet. By systematic engineering, we mean a general purpose way of thinking about biology as a technology, regardless of what application you might be interested in, such that if you gain access to this approach, no matter what you want to do in the future, you have a chance of getting underway. In slightly more detail, the goals we have for this class include the following three. To help you learn these ways of thinking about engineering living matter from the inside out, as you'll see. To empower you to explore and do bioengineering, starting with DNA. We think of this like literacy. Do you know how to read and write in English or whatever language you like? Do you know how to read and write in Python or another computer programming language? There we talk about literacy or computer literacy. Do you know how to read and write DNA? That would be bioliteracy. So we want to empower you to start to become literate with biology at the DNA level. And then third, for you to become more capable of leading discussions about bioengineering with others. Stated differently, hey, if you get an A+ in Introduction to Bioengineering, almost by definition, you should be able to introduce somebody else to bioengineering, right? So that's what we mean about becoming more capable of helping others, leading discussions about bioengineering. And not just the nerdy stuff, but the really tricky stuff, like the social and cultural and political and ethical aspects. So that's what our class is about. But it's also sort of motivated from a more basic foundation. And so I want to give you an example of how Professor Brophy and I are thinking about why our class should be organized in a particular way and how we hope to relate with you. As one example, Neil Postman was a critic, author, and educator, and he had a lot to say about education. I take what he says as provocations to help me think about what we're doing in this course. For example, how's this for drama? The basic function of education is to increase the survival prospects of the group. What should you be learning now in case an asteroid hits the Earth next year, right? Or another pandemic shows up, or who knows what's going to happen, right? That's the basic function. This sounds strange. Has any teacher told you this is why you're coming to school in case the asteroid hits the Yucatan? Maybe not. It's like just kind of dramatic, but it's interesting to think about. Continuing on, it's one thing to survive if nothing's changing. But if the world's changing, the environment's changing, is changing quickly, then from an education perspective, it's trickier because you've got to figure out what of the existing knowledge do we need to make sure everybody keeps and learns, and then what are the old ideas we need to get rid of, and then what new things do we need to learn about? So now that brings us back to bioengineering. Bioengineering is a new and emerging field. And so education in bioengineering is going to have to figure out, how do we navigate these changes and these fundamental goals? Stated differently and more practically, bioengineering matters a lot. It already matters a lot, and it's not getting less important. It's getting way more important. Therefore, as teachers, we're with you. We're not trying to make the hardest P-sets possible. Like, they'll be challenging, but we're not like at you trying to oh, you're not as smart, No. We just want you to learn as much as possible because it's going to matter. The more you can learn, the better we're all going to be. And so we want to see you as people first and to help you learn as much as possible. So hopefully you just reflect on this and have a sense of how Professor Brophy and I are thinking in our own minds as we're building the course and learning together with you. Now, I want to switch gears and end with just one comment. And this is already in service of the third goal, to help you lead others in discussion about bioengineering. And I want to be really clear up front. I'm going to say some things that might seem like they're critical, as I don't mean that. I'm just observing and trying to give you some context to help understand the uniqueness of this course, Intro to BIOE at Stanford. What you see here is rankings of graduate programs in bioengineering according to a magazine, U.S. News and World Report, from 2019, about 4 years ago. What's really interesting at first glance, I'm sure everybody can see, on the left side is bioengineering, and on the right side is biological engineering. How come there are two different rankings? And what's the difference between bioengineering and biological engineering? And does it matter? Well, it turns out that these rankings and the split of the rankings comes from the past. It's really a 20th century framework for how people were thinking about bioengineering. if you were a mechanical engineer or an electrical engineer and you got a call from a doctor who needed help with a patient who needed an artificial knee, or you need to make a better x-ray machine or an MRI machine, you'd find yourself working in a clinical setting to help the health enterprise, and you'd be a bioengineer. But that's shorthand on the left for biomedical engineer, right? An existing type of engineer helping with a medical need or application. Conversely, on the right, you're a mechanical engineer or an electrical engineer or a civil engineer making a better tractor, making a better brewery, or making a better wastewater treatment plant, right? Then you're taking the skills of engineering and helping people working in manufacturing, farming, and related things. And that becomes biological engineering. Stated more abstractly, these two rankings reflect the needs of the world and existing engineering disciplines being organized into institutional programs that are doing incredibly important work. Like, this is absolutely essential for excellence in both bioengineering and biological engineering. But it's this outside-in framing that is, just like kind of, just say 20th century. So with love and respect, I'm going to put a big X right there. Let's go into the 21st century. This is a watercolor painted by David Goodsell. It shows the molecules comprising part of a bacterium, E. coli. What our course is about is to start with the physics of living matter, the molecules that comprise life, from the inside out. And if we can learn how to systematically engineer biology from this starting line, then when we get out into the real world, it doesn't matter what we need to do. Any sort of application can be accommodated and addressed. And so that's what we think of as 21st century bioengineering going forward into the future. We'll come back and look at these paintings, but just to give you a clue, like that green set of lines on the top left, that's the membrane dividing the cell from its inside and outside. Hidden in that is a motor for spinning around the flagella, which is the tube heading off to the left that pushes the cell through liquid. In purple and blue are ribosomes and proteins in the cytoplasm. Look at how crowded it is. In orange and yellow, you can see DNA and RNA and replication of the genome. If we can figure out how to bioengineer from the inside out with life, then everything that life can be becomes possible for bioengineers. Until next time. Welcome to Introduction to Bioengineering at Stanford University. This is a short little tool that's great at the start of class. It's called Imagine a Bioengineer, Imagine Your Bioengineer. This tool comes from Dr. Veronica Brand, past colleague, amazing educator, super grateful for her help in developing the materials in this course and others in bioengineering. So let's get started. Again, this is a tool, an exercise you should do towards the beginning of class, and we'll do it again at the end of class if you like. Imagine a bioengineer. Now you're going to need, in a minute, pencil or pen and some scrap paper or paper. So take a moment to get that. And once you have that, the first thing to do is close your eyes, just relax, and imagine a bioengineer. Now, it's a little bit strange because it's the beginning of class and maybe you're not sure what a bioengineer is. Nevertheless, just relax and, well, what's a bioengineer? What do they look like? What are they doing? What's the scene they're in? When you stop and try and imagine a bioengineer, what comes to your mind? Take as much time as you like on this, but then once you're feeling good about it, go on to the next step and use your paper and pencil and just draw a sketch. Simple stick figure, whatever, however you like to draw. Draw a sketch of the person. Where are they? What do they look like? What are they doing? What's around them? Take a few minutes, get that sketched out, and when you're ready, move on to step 2. When you think about what you've imagined and what you've drawn, just write down 3 different words that describe the bioengineer you imagined. Characteristics, anything about them that comes to your mind. Great. Next step. Take a look at what you've drawn. This is an example from Veronica. Is that what a bioengineer looks like? Well, that's what she imagined. Looks like they're working at a bench. Maybe they've got safety goggles on. It's interesting. What were the words? A bioengineer is creative. Bioengineer is logical. A bioengineer is a problem solver. There's no right answer here. The exercise is just to get you to imagine what a bioengineer is at this point in the course, at the beginning of things. Next, find a friend, if you can, pair up, and share your drawings. Compare both bioengineers that you imagined. What's the same? What's different? On a scale of 0 to 100, where 0 is totally different and 100 is exactly the same, how different or alike are the bioengineers that you imagined? Again, there's no wrong or right answers, just trying to orient you and begin to imagine what a bioengineer is. And that's it. However, at the end of the class, we're going to come back and do this again. If at the start we imagined a bioengineer, at the end of the class, your job will be to imagine your bioengineer, what you think a bioengineer is, after you've taken the entire class. And I don't want to spend too much time on it, but I'll do a quick reveal of what Veronica came up with at the end of class when she created this exercise for you. A lot more is going on, and maybe a lot more interesting. We'll see what you come up with in a couple months. Today we're going to explore the question, why engineer biology? This question is meant not as a prescription, but really as an invitation for you to explore and reflect on what's going on. You oftentimes hear in movies, just because you could do something, should you do it? And so in the spirit of that reflection, let's explore how engineering and biology come together. My name's Drew Endy. The slides are from me. Any mistakes or comments, let me know. There's my email address. Just send me a note. The thing that's so interesting about bioengineering is biology becomes apparent well before engineering. I love this movie, Growing is Forever. A short little film, you can find it online. And it's a representation of what you can find in the woods around Northern California. None of this has anything to do with bioengineering, right? This is all something that exists before Homo sapiens come around, humans come around and start doing things. In other words, the planet is full of life. It's full of biology. And it's amazing and wondrous and sacred and many more things you could give name to. So think about this when we think about why engineering biology. So once upon a time, until one day, some of the biology, the human part, started happening to the rest of the biology. There's many ways to illustrate this. Here's one of a few examples. Take a look at these fruits and plants on the screen, the 3 up top, the 3 down below, and see if you can figure out what they are. I'm sure many of you are familiar with many, if not most, or all of these plants. Watermelon, eggplant, carrot, banana, corn, broccoli. These are the natural ancestors of these plants before they were adapted by our ancestors through a process of domestication and breeding to make the modern forms we're familiar with. So teosinte becoming maize, becoming corn. Look at what's in the bottom middle. There's no cob, there's quite a small number of kernels, and so on. So one day, we started happening to biology, we, humanity. Why? Well, one of the reasons is we depend on biology for many things, starting with food. So here's a fabulous meal, the First Nations fall celebration. Industrial agricultural today in the United States gets us to a lot more, right? So we're now the largest global exporter of food. This is, in other words, shaped the relationship between human and biology because we care about what biology can make, because we increasingly depend on what biology can make. We're going to change the biology. historically through domestication of plants and animals. More recently, over the last couple hundred years, but especially over the last 100 years, the science of biology has become so interesting. For example, Barbara McClintock in the middle here, she studied maize and corn and how sometimes corn on the cob, you get different colored kernels, and linked this back to the idea that some genes can jump around on the chromosomes, so-called jumping genes or transposons. More recently, a fourth generation DNA editing tool, famously known as CRISPR, was discovered and then invented. And it's just so incredibly interesting. By the way, if you want a funny little thing to remember, the scientist down below, Jennifer Doudna from Berkeley, look at her last name carefully. I bet you could impress your friends or parents just by remembering how to spell her name. DNA. Kind of cool. Now, if we get bountiful manufacturing and growing and science, the next thing that follows, remember, this has nothing to do with us yet. This is all before our time. What follows science is often technology. And so, for example, this is a United States patent issued in 1980 to Stanford University. And if you look at the title of the patent in the top left, process for producing biologically functional molecular chimeras. What the heck's that? What that means is you can take different molecules of DNA and cut and paste them to make a composite or chimeric molecule. This is part of the birth of genetic engineering in 1980, over 40 years ago, right? Now, once you get the ability to intentionally intervene in genetic material, see, breeding and domestication, that's sculpting from the outside of the traits of a plant or animal, back in. But now we're going from the inside and trying to figure out what could happen when we make changes and then the animals show up or the plant shows up. If we can begin to do that, then we're going to have a whole other sort of approach to economic activity. And this can be represented, maybe you've heard of the gross domestic product as a measure of the economy, how much dollars there are, being produced in goods and services. You could look at a subset of that and call it the genetically engineered domestic product, or the GEDP. And what's shown here over time, starting in 1980, around when this patent comes out, going out to 2017 for what the data is available, you can see that the plots are going up and to the right. And so what that means is the amount of money made in the United States by genetic engineering organisms is increasing over time, or at least it has been increasing over time. And this is because of three major types of products or services. In green are genetically modified organisms, cotton or corn or soy. In red, those are biologics, those are medicines. And then in blue is industrial intermediates. Because this is kind of abstract, I'll give you examples on the next slide. But the takeaway here is, wow, suddenly in 1980, we're getting a tool. For the first time, we can begin to engineer biology from the DNA outwards. And almost immediately, you start to see this growth of a bioeconomy. And one thing you can think about later is, how long does it take for the bioeconomy to double, say from $100 billion a year of revenue to $200 billion a year of revenue to $400 billion a year of revenue? Think about where that's going. It's already a huge number, by the way, but think about where it's going. But let's look a little bit more about what these different, types of products and services are. So on the top right, we have an example of genetic engineering for medicine. You can take a gene that encodes a protein, insulin, and modify a bacteria so that the bacteria makes the insulin for treating diabetes, as opposed to having to harvest insulin from the pig's organs. Or on the bottom left, you could see a papaya that's suffering from a virus infection, in this case, the ring spot virus, as shown in the inset. And Dennis Gonsalves and others figured out that you could genetically modify the papaya so that it could be immune or resistant to the ring spot virus. On the top left, we see this oily yellow material. I believe that's farnesene, an industrial intermediate compound. But what's interesting is where the farnesene is coming from. It's not coming from a barrel of oil or some other thing. it's coming from bioengineered yeast, which are the bluish gray circles, much smaller here. And they've been engineered to take glucose or sugar in, and instead of making wine or beer, they're making this oily substance, farnesene. Right? Whoa. Bottom right, you see what looks like an animal hide, a leather or something like that. But that's not what it turns out to be. It's a replacement for those types of materials. And instead of being made from a vertebrate, a mammal, it's made from something like this, from a mushroom. And it's growing from wood chips or sawdust. Very interesting. So that's when we talk about food and medicines and industrial intermediates and materials, these are examples of what's in the bioeconomy. It's not all awesome, right? So let's just go to the other side of the coin really quick. Humanity's relationship with biology, it's booming in terms of biotechnology and the bioeconomy, but a whole bunch of things, some of which you're obviously familiar with, but others might be a little bit esoteric, are not going well at all. Right? So everybody's experienced the pandemic. The word pandemic literally means all people. So, like, how about we make that not happen evermore? But what about pollution? If I've got industrial agriculture and I'm fertilizing the fields and I have runoff through the rivers, and then suddenly I get a lot of nitrogen and phosphorus in the estuaries, I might get overwhelming algal growth. Or, where do I grow these crops? This is an oil palm plantation on the top right. And to grow oil palms, I have to displace the jungle. And if I displace the jungle, then where are the natural creatures going to live? Probably nowhere, which is causing, top left, increasingly things to go extinct besides humans, right? So over my lifetime, the human population has doubled, but natural biodiversity seems to have gone down by a factor of 2. So begs the question, if we've had this relationship with life that predates us, growing is forever, not totally clear that's a done deal. This is a shocking photograph of a wildfire in California, only about 30 miles from the Stanford campus near Santa Cruz, California. So is growing forever. How does this then take us to, Martin Luther King Jr. and his most famous speech? And so when you think about bioengineering, for me at least, I think it's impossible to think about bioengineering without thinking about what we wish for. And just to say what this speech was not about, I bet everybody knows this, but I'm just going to say it so we know what it was not about. This very famous speech was not about, I have a degree, or I have a vaccine. This speech was not about, I have a petri dish for doing experiments. Not at all. It was not, I have a it was about none of the things we've been talking about, at least not yet. This speech, as we know, is, I have a dream. Now, what's this have to do with bioengineering? We'll see. It turns out, from an engineer's perspective, we can think of dreams as a type of technology in and of themselves. In other words, dreams are tools. Now, what do we mean by this? A tool has to be good for something. So what are dreams good for? Dreams can be the tool we use to make sure that we're happening to things. Well, what does that mean? We can use dreams to organize ourselves and others. So are you happening to the future, or is the future happening to you? Are you happening to the world, or is the world happening to you? Are you happening to artificial intelligence research, or is that happening to you? Oftentimes in the world, it feels like, because it's true, things are happening and just everything's like crashing on us and the world's happening to us. But if we think about dreams as tools, we can use these sorts of approaches to make sure we're happening to the world, we're happening to the future we wish for. Is bioengineering happening to you, or are you happening to bioengineering? So if you want to, determine your answer to that question as opposed to just let whatever happens, maybe you'll find this next little section interesting. Now, dreams come, I'm not going to make this too complicated. Dreams come in a couple different flavors. The easiest to understand is the nightmare or the negative dream. It's like horrible. A lot of times when we use dreams as tools, we use negative dreams because it's easier to get attention by shouting about the bad thing. The boy who cried wolf. even though it's easier to get attention and to get people to react, the problem with the negative dream is if enough people don't believe the bad thing's real, you won't get anything to happen, right? Stated differently, you have to get enough people believing that the bad thing is real before you get enough action. Now, this is going to sound really strange, but what if, we've been living in a negative dream about climate change for longer than we can remember, and because it's a negative dream and not everybody believes climate change is real, it's making climate emergency inevitable. Right? It's like a double nightmare. It's like we have a bad dream about the future, and then because of that, the bad future is even more likely to happen. Let's see if the data supports this way of thinking about it. So we'll go back in time, 110 years ago or so, 120 years ago. You can find in the newspapers articles about how burning coal will eventually cause the Earth to boil all the oceans because it's going to become so hot. Or in popular mechanics, it's just a couple centuries, going to get way too hot. All right, I guess we knew that, this bad future, this bad story about the future. But we didn't do anything about it yet. Fast forward 1989, 2006, Vice President Gore is very concerned about climate change, making an incredible slide deck and then a documentary, An Inconvenient Truth. And you can see right there in the subtitle, a global warning. He's telling a story about the future based on his understanding of what's happening, and the future isn't going to be good. And he's taking a negative narrative approach to spur us into collective action. Did it work? Not obvious. Maybe not enough people believed that it's real. How about we fast forward to this decade? Here's a great book, Speed and Scale, a global action plan for solving our climate crisis now. See that? Our climate crisis. The negative thing is starting to become real. And because enough people are starting to believe, look at all these other names on this book, Bill Gates, Jeffrey, Christina, wow. Because enough people are now believing the negative thing is real, maybe we can get to collective action. Here at Stanford, we've seen that. John, the author of that book, and his wife helped underwrite a new school at Stanford, the School of Sustainability. Amazing, right? Maybe just in time. What language is so curious to me. What's interesting about the School of Sustainability is if you turn it into an acronym, what do you get? SOS. That's the signal that is broadcast when a ship is sinking. Save our souls. We're going down, right? So see how over 100 years, by telling a negative story about the future of climate, eventually we're getting to the emergency becoming real, and now we've got the SOS signal being broadcast. Here's the good news if you're interested in bioengineering. If you ever happen to be on a ship that's sinking, I would encourage you to put on a life jacket and go to lifeboats. Life jackets, lifeboats, life. Oh, that's biology. That's the living stuff. That's bioengineering, maybe. Now, enough about negative dreams. Let's talk about positive dreams. Positive dreams, if you can pull it off, have a chance of enabling collective action in advance of reality. And going to the moon is an example of a collective dream. Martin Luther King, I have a dream that's a positive, aspirational dream in advance of reality, right? It lets people work together before, the hard work of making something really fabulous, gets all figured out. It's harder to do, maybe. And it's funny to think about in the counter examples we were just giving. Like, instead of climate change, making climate crisis, making climate emergency, could you reframe that and say, wow, hey, everybody, we've got a climate opportunity. There is so much carbon in the atmosphere. What can we do with all this carbon in the atmosphere? And gosh, if we have a climate opportunity, I have a dream. It's called Climate Awesome. Let's all work together to make climate awesome. Because I bet each of you has grown up in a world that doesn't use this language at all and just talks about climate change and climate emergency and climate crisis. I hope these words, when flipped around, feel a little bit strange. And that should be a clue to you that there's a choice to make in terms of how you architect a dream. I want you to think about this question too, and then we'll move back to bioengineering. Is it harder to articulate a positive dream? Is it harder to make it real? And if you want a clue about this, go back and read the history about the I Have a Dream speech that Dr. King gave, and see if you can track down the link in the bottom of this photograph here of Mahalia Jackson and her role in contributing to the speech as it was presented that day. Incredible story. I'll let you follow up on as you like. So now let's bring it back to bioengineering. What are our positive dreams of and with biology? If you got nothing to say to this question, no problem. Maybe you're going to do something else besides bioengineering. But if this question resonates with you at all, or if you care about the answer, then maybe that's a clue that you have something to contribute to bioengineering in the future as manifesting via bioengineering. I love this photograph of a boy, looks like he's fishing on a creek somewhere in India, in part because not just of the boy and what he's doing, but because of what's behind the boy. It looks like a suspension bridge. But this suspension bridge is not made out of concrete and steel. This is made out of the roots of a rubber tree. And is so incredibly interesting to me because, it doesn't emit carbon as the concrete is curing. It actually fixes carbon, and it gets stronger over time, and it can be passed down from one generation to the next. It's a totally different way of building. It's a way of building called growing. What if biology was the ultimate way of manufacturing because it was nature's way of manufacturing via growing? We'll come back to that in another lecture. Do you have a positive dream of and with biology? What I can offer you really quickly is some facts. We know biology is all over the planet. It's in most places. We can quantify how much energy it captures from the sun via photosynthesis. The answer is 90 terawatts. A terawatt is 10 to the 12th watts. What's 90 terawatts, you should be asking? All of human civilization today is running on about 20 terawatts. So you know that 90 is 4.5 times bigger than 20. Stated differently, if you're understanding what that means, in nature itself, there's an energy harvesting capacity sufficient to make things at about 4.5 times as much as all of humanity's running on. It's like, whoa, there's a clue there. Like, I have a dream. We should be able to flourish on this planet with everything else. Like, just that 90 terawatt fact makes that seem plausible. We also know as facts that biology reproduces, it grows, the materials heal. Very functional material, right? You can make a structure, you could sequester metals, you could grow a fiber optic cable with a sponge in the ocean, right? We also know that life matters, ramifications, right? It's like very important what's happening with life, let alone anything we do with life. So, we could adjust the facts a little bit, but not too much, because the facts are the reality of the planet and life on the planet. What's up for grabs, though, is anything you put on the right of this slide. So here's my offering, but it's not a prescription. Like positive dream. Let's enable 10 billion people to flourish, provide for themselves, ourselves. Let's do that in a way that doesn't trash the place. Let's stabilize and recover natural biodiversity. Let's make infectious diseases obsolete, and might as well make other diseases obsolete too. Let's take them off the table. There's a choice here in terms of how we develop biological futures. Am I a citizen of that future? Are you a citizen of that future? What about your kids? What about your grandkids? Or are they only consumers in a biotic future, or subjects or objects or something worse still? I also have a dream that by building with biology, we'll learn how natural living systems work a little bit better. You could take a bicycle apart, you kind of understand a bicycle, but if you put a bicycle together, I bet you'd understand the bicycle a lot more, right? And so learning by building is a nice outcome, perhaps, of bioengineering. Again, what's on the left are the facts. What's on the right is an example, not a prescription. And I encourage you to discuss and debate what should be on the right of this slide. But most of all, in the context of dreams, please, if you're going down this path, go for a positive dream, right, towards the thing that's aspirational that we can work on collectively. What's so interesting beyond the initial bioeconomy data is the fact that even though it's booming, and it's like 5% of the economy already, mostly doesn't exist. Like people haven't imagined most of what biology could be. Here's one of my favorite recent examples. This is work coming out of London, England, and Moscow, Russia, and a US company. And these are plants. Now, when you think of plants as harvesting light and fixing carbon and emitting oxygen, these plants do that, but they've been engineered, they've been bioengineered in addition to also take some of that sugar that they make and turn it back into light. So if the plants are in the dark, they glow. Now, if you bring one of these plants home, and put it on your bookshelf or your dresser, and it's dark in the room at 3 a.m, you'll have a nightlight. But instead of plugging the nightlight into the electrical outlet, you're watering it because it's alive, right? Like, okay, what else could we imagine bioengineering with living systems? Now, back to introduction to bioengineering, if you had to learn everything about everything in biology to be a bioengineer, it's not going to be very valuable. And one of the things that's so neat about now is the science of biology has gotten us to a starting line where we think we know enough about biology to have a general purpose bioengineering discipline. Historically, let me try and make sense of it by going back in time and thinking about the beginnings of computer science. There's a neat quote that used to be on a building here on the Stanford campus from 1961. Enough is known about the diverse applications of computing for us to recognize the birth of a coherent body of technique, which I call computer science, whether computers are used for engineering design, or medical data processing, or making music, or anything. The structure of computing is pretty much the same. It doesn't change, right? Now let's just update this for bioengineering. Enough is known about the diverse applications of biology for us to recognize the birth of a coherent body of technique, which we call, wait for it, bioengineering. Whether living matter is used for manufacturing, making medicines, abiotic data storage, that means putting the library inside DNA, making bioart or other purposes, the structure of engineering life from the inside out is much the same. Now we're going to have to see if this is true and prove it to you and then enable you to practice it, but that's the gist of what's going on that makes bioengineering interesting in thinking about why now. I'll give you a totally different example coming from social media. Seemingly random tweet from almost 2 years ago. Synthetic biology is about to undergo a Cambrian explosion, says Eric Schmidt at a meeting somewhere in Boston, it looks like. Now, Eric Schmidt's well known for being the CEO of Google when Google became a very big company. And now he's thinking about synthetic biology. What's synthetic biology? Synthetic biology is a suite of tools we'll see in another lecture relating to how people do bioengineering. And he says it's about to undergo a Cambrian explosion. Now, the Cambrian explosion is relating to a point in the history of life on Earth where over a period of 10 or 20 million years, you got a tremendous diversification of animal and body plants. So put all this together, like what's going on here? How do we interpret this? Option one, since the Cambrian explosion took 13 to 25 million years, maybe what Eric means is that biotechnology is going to take another 13 to 25 million years to mature. In which case, if you're in high school or college, you want to come back in 20 million years. Good luck. I don't think that's what Eric means. I think what he means instead is that the underlying approaches that will unlock all the possibilities of biotechnology, those approaches are being worked out now in real time over the last 10, 20 years and this decade, such that by or before 2030, you're going to see biology become a general purpose technology, just like computing became a general purpose technology. And so what that means is in terms of why bioengineering and why now, it's looking pretty interesting. Looks like there's a lot at stake. We see that reflecting back from the government. So here is an executive order from the 12th of September of 2022, signed by President Biden. Let's look at the title of this. Now, an executive order is the president is instructing the executive branch of the government to do certain things. This is an executive order on advancing biotechnology and biomanufacturing innovation for sustainable, safe, and secure American bioeconomy. And if you just, I'd encourage you to read the whole thing or skim it if you like. The policy here is to take a whole of government approach, like all hands, the entire federal government, everybody has to figure out how to advance biotechnology and biomanufacturing towards innovative solutions in health, in climate change. Oh, note the negative there. In energy, in food security, that sounds positive. In agriculture, in supply chain resilience, positive dream there. In national and economic security, mixed. Central to this policy and its outcomes are the principles of equity, ethics, safety, and security, enabling access to technologies, processes, and products in a manner that benefits all Americans and the global community, and that makes sure USA is winning or in the lead, or at least competitive. I'm paraphrasing. Well, that's interesting. like all hands, says the White House just a few months ago. If you go back, not even as far, to October 18th of 2022, the administration is this time releasing a national security memorandum, number 15 from their term, I guess. And this one's called the National Biodefense Strategy and Implementation Plan for Countering Biological Threats, Enhancing Pandemic Preparedness, and Achieving Global Health Security. Within this document, my favorite part is the vision. This is akin to the dream. It reads, the United States actively and effectively assesses, prevents, prepares for, responds to, and recovers from naturally occurring, accidental, or deliberate, we're going to have to come back and talk about that, biological threats impacting humans, animals, plants, and the environment. And here's the best part, creates a world free from catastrophic biological incidents. So let's just simplify. The United States creates a world free from catastrophic biological incidents. Sounds to me like no more pandemics, right? Well, we're not there yet, but that's a nice dream, right? Maybe. Interesting. In any case, here's evidence that something is afoot. Something is afoot at the biggest scale, on the grandest stages. Bioengineering is contributing and becoming something unlike anything we've navigated before. Which brings us back to where it started. What does it mean to be a bioengineer? Should we be bioengineers? We're not yet anywhere as capable of the things that we see here in nature. Yet each thing we see in nature is a point of inspiration, a point of instruction, a point of empathy. It's not really a point, it's more like a web, or a connection, or a story, or something we are still going to figure out. So I hope these remarks give you an on-ramp for yourself to think about why bioengineer. Let me offer some very, accessible questions, I hope. Do you think it was inevitable that Homo sapiens would start to adapt and change living systems? Should we keep going? Could we stop? If you look at the plot on slide 6 around the bioeconomy growing, could you estimate how long it takes the bioeconomy to double historically? Like how many years? And if that trend continued, how big would it be in 30 years, say 2050 or whatever time you like? One of the things about bioengineering, as mentioned, is mostly hasn't been imagined yet, those glowing plants or who knows what else you could think of. So you could practice inventing the future. Why don't you give it a try? So here's an example prompt. In a flourishing future, there is a biotechnology related to libraries. What is it? Just go invent that future thing. A biotechnology related to libraries in a world where everything's working really well. And if you like this type of prompt, see the little words I put in parentheses, flourishing and libraries. You could change that to, in a catastrophic future, there's a biotechnology related to yogurt. What is it? Right? Just feel free to play with those words and keep inventing biotechnological futures and see what you can come up with. Reflective question 4. And again, reflective questions. These are not homework per se, and just things to get you to think about what we've been talking about in the slides here. If you zoom out and think more broadly, we saw that there was food, medicine, and industrial chemicals as the big 3 slices of the pie for the bioeconomy. Is that all there is? What if you went to this point in the future after you do some invention? Could you come up with entirely new sectors of biotechnology? Which ones would you like to pioneer? Question 5. Setting aside all the economic stuff and the security stuff, if you just take a step back and imagine the world you wish to live in or contribute to or both, as it has to do with biology, what do you wish for? What are your, emergent dreams? Things that biology could or should become or should not become. And then zooming out still further and thinking about dreams as I know it's a bioengineering class, but wow, one of the things from today is dreams are tools, right? If you can understand that, you've got a super powerful tool in your toolkit for causing things to happen or not. So thinking about that, dreams as tools. The world you live in now, what bigger picture dreams coming from outside you, coming from other people, whether they're good or bad, have nothing to do with biology, but are defined by other people. What dreams are you experiencing, right, that are shaping the currents and contexts in which you're navigating?
Eternal youth, Spaceships for everyone. Necromancy.
That's it for today, and can't wait for next time.
All right. Bioengineer biology. All right, I'm getting kind of sleepy. All right. Cut it off there.